11.5, exploring solid. Vocabulary to start out. First of all, a polyhedron. A polyhedron is a solid that is bounded by polygons called faces. You see the faces right here. So each one of these faces, so here's a polyhedron. Each flat surface, two-dimensional flat surface, is a face that bounds, that makes boundaries to form a polyhedron. And each face, where two faces meet, we have an edge. So I have a face, and it makes an edge. An edge is a line segment formed by the intersection of two faces. And then when you get three faces together, or three edges, they form to make a vertex. So you would have at least three. So you could have more than three, but at least three will get a vertex. Here are some types of polyhedrons and not polyhedrons. Remember, a polyhedron, or polyhedra for plural, is polygons that are formed together. I have all polygons here. Remember, if you have something rounded, it's not a polygon, so it can't be a polyhedron. So here I have circles. If I have any rounded shape, then it's not a polyhedron. Classifying solids, it's the first thing we're going to do. One of the 5 solids above that we just looked at, the prism and the pyramid, are polyhedra. To name a prism or a pyramid, we use the shape of the base. The base, what it sits on. For instance, this shape right here is sitting on a pentagon. So this would be called a pentagonal prism. Pentagonal, pentagonal, I'm not sure. Actually, I think pentagonal probably sounds the best pronunciation, but just do your best. So the two bases of a prism are congruent polygons in parallel planes. So these are congruent polygons. They are in parallel planes, so they would be the base. Here I have the base of the pyramid as a polygon. So here I have a triangular pyramid because the base is a triangle. Tell whether the solid is a polyhedron. If it is, name the polyhedron and find the number of faces, vertices, and edges. Here, this first one, A, it is a polyhedron, and because the base is, if I set it on any different base, the base would be a rectangle. So it is a rectangular prism. Okay, the second one, the base is 6-sided. So it would be a hexagonal pyramid. And part C is not a polyhedron. So in A, I've got 6 faces. 1, 2, 3, 4, 5, 6, 7, 8 vertices, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. Here I have 1, 2, 3, 4, 5, 6, 7 faces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. And 1, 2, 3, 4, 5, 6, 7 vertices. Very cool. Okay, why don't you try this? I'm going to push pause and you can finish it on your own. Okay, check out your answers. See if my answers agree with your answers. If not, that'd be a great question for you to ask tomorrow. Alright, notice in earlier examples that the sum of the number of faces and vertices of the polyhedra is 2 more than the number of edges. It's chore day in the Shellhammer household, so we are yelling at the children to do their chores. Sorry you had to experience that, but it is sort of funny. This right here is, I've always pronounced it Euler's theorem, but I looked it up, and it actually is pronounced Euler's theorem. So I'm going to do my best to pronounce it correctly, Euler's theorem. So the number of faces plus the number of vertices equals the number of edges plus 2. If you look at this, I have 6 faces, then 1, 2, 3, 4, 5, 6, 7, 8 vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 edges. 6 plus, sorry. Oops. 6 plus 8 is, so 6 plus 8 is 14, 12 plus 2 is also 14. Okay, use Euler's theorem in a real-world situation. Find the number of edges on the frame of the house. So if I count the number of faces, I mean this right here is a face, 1, I'm going to erase that. We'll just do this. This right here is 1, the back side is 2, I have the right side and left side, 3, 4, the bottom 5, and the roof 6, 7. I think there's 7. 7 faces, vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't think I forgot any. We have 10 edges. I just call those edges, they're vertices. 10 vertices. So if we use our equation, faces plus vertices equals edges plus 2. 17 equals edges plus 2 minus 2 minus 2. The number of edges equals 15. Let's try to count it just to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Cool, got it right. Regular polyhedra. If a polyhedron is regular, a polyhedron is regular if all of its faces are congruent to regular polygons. A polyhedron is convex if any 2 points on its surface can be connected by a segment that lies entirely inside or on the polyhedron. If the segment goes outside the polyhedron, then the polyhedron is non-convex or concave. If you look, if I connect any 2 edges with a line segment and it is outside of the polyhedron, then it's concave. We've always talked about in the past that if anything is an indent or indented for the polygon or the polyhedron, then it's concave like a cave. If I connected any 2 sides in this one, my segments are always inside the polygon, so it's regular convex. There are 5 regular polyhedra called Platonic solids. I have a regular tetrahedron, which is 4 faces, a cube, a regular octahedron, which is 8 faces, a regular dodecahedron, which is 12 faces, and a regular icosahedron. I did not look up how to say that. I don't know if it's iso or ico, with a C and an S in the word. I would assume the C would be hard. So icosahedron, not sure. But those are the only 5 regular polyhedra that exist. Find the number of faces, vertices, and edges of the regular octahedron. Check your answer using Euler's theorem. So number of faces, 1, 2, 3, 4, 5, 6, 7, 8. The number of vertices, 1, 2, 3, 4, 5, 6. The number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's check. 8 plus 6 equals 12 plus 2. 14 equals 14. We're good. Next lesson, cross-sections. Imagine a plane slicing through a solid. A plane is a piece of paper, right? And if it's sliced through a solid, the intersection of the plane and the solid is called the cross-section. Okay, I've got a piece of paper that cut this pyramid at one point, and the cross-section I'm coloring in right now, the cross-section for this is a triangle. Example, describe the shape formed by the intersection of the plane and the cube. A cube is a bunch of squares put together. So in part A, the cross-section would be a square, right? In part B, if I'm cutting the same cube, but I'm cutting it on a diagonal, the cross-section would be a rectangle. Describe the cross-sections. Part C. This is still a me-do. The same cube, but I'm sort of cutting it on a slant, and my cross-section looks like a trapezoid because this line and this line are parallel, and these two are not. Find the number of faces, vertices, and edges of a regular dodecahedron on page. I did not cut that thing over. Check your answer using Euler's theorem, sorry. Let me look at page 796. I'm pushing pause. I turned to page 796 and found nothing. So ignore that one and turn it to the next page. Okay, describe the shape formed by the intersection of the plane and the solid. What do you think it is? Okay, you're just looking at the dark purple, not the purple and blue, because the purple and blue looks like a kite, and it's not a kite. It's a triangle. Okay, this is a circle. Can't spell circle. There we go. This is a hexagon. Okay, daily homework quiz. Page 1, page 2, page 3, page 4. Good job.